So to understand why ice appeared on Antarctica before it appeared in the northern hemisphere, we need to consider some of the polar geography. Okay, so here's some maps of the world that you might not be used to seeing. So this is a map of the northern hemisphere looking straight down on top of it. And this is a map of the southern hemisphere looking kind of straight up from the bottom. And so what we notice right away is that in the northern hemisphere, right around the North Pole, most of the area inside the Arctic Circle, which is shown in this dashed blue line here, most of this area is ocean. In contrast, in the southern hemisphere, the continent of Antarctica sits entirely within the Antarctic Circle, again, this dashed blue line. This is important because we know that sea ice is not as stable as continental ice, right? So sea ice is floating on top of liquid ocean underneath it. And so that ocean's always moving around and circulating. And so it makes a very unstable foundation for that sea ice. And so sea ice has a harder time sticking around. We know from that video that NASA released, right? We can see the sea ice expanding and contracting with the seasons. Ice that forms on continents is much more stable because it's got this solid foundation that it can sit on for a very long time. Okay, back real quick to the Arctic and Antarctic circles. Again, these circles with the dashed blue lines. So these represent the parts of the Earth that receive either no sunlight during the winter or total sunlight during the summer. And of course, those are opposite for the North and South poles. Okay, so here's June, summer in the Northern Hemisphere. You can see that everywhere in the Arctic Circle is always pointed towards the sun, no matter what time of day it is. This dashed line here is the Earth's axis of rotation. So if you're standing at the Arctic Circle, you just rotate on this plane, and you would rotate all the way around until you were at the very, very top of the Earth, seeing the sun exactly on the horizon, right? So during the summer, you've got total daylight. And at the same time, in the winter, in the Antarctic Circle, you're in total darkness. And of course, that's flipped around for the northern and southern hemispheres in the summer and the winter. So winter in the northern hemisphere is the same thing as summer in the southern hemisphere. So that means that in the southern hemisphere winter, over here, Antarctica is in total darkness. It's very, very, very cold there, right? So ice can accumulate. But in the summer, it's constantly getting hit by sunlight. So how come all that ice doesn't just melt back every season like the sea ice does? Well, we already know that sea ice is not as stable as continental ice, but now we want to kind of move forward and think in more detail about what are the factors that control the growth or the retreat of continental ice sheets. So what controls whether or not continental ice will grow or retreat? It's a pretty simple idea. First, we should just know that when snow falls, if it sticks around long enough, right, if it doesn't melt right away, eventually that'll become compacted into ice. So when glaciers and ice sheets are able to grow, that's when the accumulation of snow and turning into ice is greater than the amount that's lost due to melting. Pretty simple. Now, places where accumulation is greater than melting are places where the average annual temperature is low. That's the average annual temperature. In general, average annual temperature gets lower the closer you get to the North and the South Pole. So if we look over here at this diagram here, we should remember that the poles are colder than the equator because of the uneven distribution of heat on the Earth's surface, right? So more light gets reflected near the poles, there's a greater albedo, and also the same amount of sunlight is spread out over larger areas, right? Remember from video 3.2? So as you go towards the poles, your average annual temperature gets lower because there's less solar energy being absorbed by the poles. And the other sort of thing you can do is you can go high, right? So if you go high above sea level, if you increase your elevation, regardless of where you are on the Earth, either by the equator or by the poles, the higher up you go above sea level, the greater altitude or the greater elevation you go to, it generally gets colder, right? So that's why mountains are commonly still snow-capped when the rest of the area around them is all the snow is melted, right? The higher you go, the colder it goes, and the further towards the north or south pole you go, the colder it gets. So if we look at this diagram on the right and think about it in terms of an ice-free Antarctica, here is a sort of topographic profile of Antarctica. You may not know, but Antarctica actually has the Trans-Antarctic Mountains that run across the middle of the continent. So there's actually some pretty high elevation right near the South Pole. So Antarctica has these mountains, and then of course the rest of it is above sea level, and eventually you come to the edge of the continent. So the left side of this diagram here is the South Pole, right? It's the exact middle of Antarctica, just about. And then as we move to the right on the x-axis, we're moving towards the equator. But remember that the further towards the pole we get, the colder we are, right? So we're moving towards the equator in this direction, we're moving to warmer places in this direction, colder in this direction. Here we've got elevation on the y-axis. This is sea level here, increasing elevation to just sort of generally high elevations. Again, with the Trans-Antarctic Mountains being sort of high elevation towards the middle of Antarctica. Okay, so if we think about this diagram in terms of an ice-free Antarctica, remember that tens of millions of years ago, before about 30 million years ago, there was no permanent ice on Antarctica. So when Antarctica started to glaciate, the very first places that would have been able to hold ice would be places very close to the South Pole and places with very high elevation. So the very first place that ice is going to be stable is going to be in the mountains of Antarctica. So we can form some ice, some glaciers here. As the planet continues to cool off, the parts of the Earth that are capable of sustaining glaciers, right, the parts of the Earth that have low enough mean annual temperatures or average annual temperatures, are going to move down in elevation and towards the equator, right, so to lower latitudes. So they're going to move towards lower elevations and lower latitudes. So that means that the ice that starts to form in Antarctica can advance and start to come further down the mountains, and eventually can sort of advance to cover most of the continent. Until it reaches the edge, until it reaches sea level, which is pretty much where the continental ice is on Antarctica today, right? And so what we see is that, remember, as we go higher in elevation, we're also getting colder. And that means that basically you can support very, very thick ice sheets, because as long as it's cold enough at sea level, or excuse me, at the sort of at the elevation of the continent, as long as it's cold enough down here, it's definitely going to be cold enough up here to sustain ice. So that means that ice sheets can get very, very thick. So the ice sheets in Antarctica are 2 kilometers thick, and the North American ice sheet that used to exist during the Ice Age was as great as 4 kilometers thick in some places, right? So these sheets of ice can be very, very thick, and they can cover entire continents. In fact, the Trans-Antarctic Mountains are almost entirely covered in ice. So the ice is so thick on Antarctica that it completely swallows up the mountains. They really only poke out of the ice in a few places. So if we make a similar diagram for the northern hemisphere and kind of compare that to how Antarctica's ice sheet would have evolved and grown, again, we can see that in the northern hemisphere, sort of starting at the North Pole and going out in all directions, you have a long way to go before you hit any land, with the exception of Greenland here, right? So there is a narrow bit of continent for ice to start accumulating on in Greenland. We've shown that with this curve here, Greenland is coming out of the ocean. This dashed line is sea level. And that's happening, at approximately maybe 85 degrees north or 80 degrees north, right about here, right? But for the other directions that you might go, you've got quite a ways to go, almost until the end of the Arctic Circle at about 65 degrees north before you hit any North American or Asian continent over here, right? If we compare that to Antarctica, we've got high mountains in the middle of Antarctica and stable continent in all directions. So we can, again, imagine that as the planet's cooling down, the poles are the first areas to get cold. Here we've got the North Pole and the South Pole, and then high altitudes are also the first places to get cold, right? So in the Northern Hemisphere, it's cold up here above the North Pole, but there's no land here, so no ice can form, right? Maybe we start to develop some sea ice, some sea ice like this. But we know that this is seasonal, right? So it's going to expand and contract, and it's not going to stick around permanently. In contrast, at the same time, we can start accumulating lots of ice on the continent of Antarctica, and then eventually this ice can sort of advance, covering much of the continent, right? And so here, right, the temperatures near the poles have gotten cold enough that the mean annual temperature required to sustain ice has sort of moved down to where ice can finally start accumulating on Greenland. Okay, but only a little bit of it can accumulate, and only right on the edge, right? Because if we go any further to the south, right, towards the equator, the mean annual temperatures aren't low enough to sustain ice, and the ice can't really just build up. You can't have like a giant tower of ice, so it's going to sort of stay low and flat here. And in contrast, we've already got tons of ice in Antarctica. So by the time Antarctica is covered, you still haven't really even gotten to the point where the northern hemisphere is cold enough to sustain any ice. So Greenland can start to expand its ice a little bit, but then by the time North America and Asia are starting to build any ice, man, Antarctica has just been covered with ice forever. Its ice sheets have met the ocean, and they're advancing into the ocean, becoming ice shelves. Ice shelves are what we call continental ice sheets that go and flow out onto the ocean where they are sort of semi-stable. So they're sort of different from sea ice. They're not quite the same as sea ice. We know that sea ice is going to sort of expand and contract seasonally. And the northern hemisphere has mostly sea ice. Okay, so with this sort of simple diagram, we can clearly see why Antarctica would have been the first to accumulate a lot of ice, and then why it took so long for ice to become stable in the northern hemisphere, because there just isn't really enough land for that ice to build on. So now we have a pretty clear idea of why ice sheets appeared on Antarctica before they appeared in the northern hemisphere. But before we move on from talking about this climate record to a new record, there are a few more details of this plot that we need to understand. In particular, I want to draw your attention to the sudden change in oxygen isotope composition of 4Ams that starts to happen once the northern hemisphere starts to become glaciated. So we notice back here that before there's ice in Antarctica, there's a sudden drop in the delta 18O values of benthic 4M shells once ice establishes itself in Antarctica. And then these values sort of fluctuate for tens of millions of years, but they actually don't really change very much within this kind of band of about 2 to 3 per mil in terms of their oxygen isotope values. Once northern hemisphere ice sheets start to appear, there's a pronounced drop, or well, actually, this is an increase. Remember, in delta 18O values, right? So an increase in delta 18O values and a drop in global temperature is how that's interpreted. All right, so once we start to see ice in the northern hemisphere, there's a big drop off and then a lot of spread. Okay, so let's explore the reason for this big drop off before we move on to anything else. To understand why the northern hemisphere glaciation had a much more pronounced effect on global temperatures than Antarctica's glaciation did, we need to understand something called the ice albedo feedback. Okay, so recall that albedo is the reflectivity of a surface. So the higher a surface's albedo is, the more solar energy gets reflected off of its surface, and the less solar energy is absorbed by that surface. And that's one of the reasons that the poles are colder than the equator. They have a higher albedo. Okay, so if we think about the albedo of some surfaces that are common in the poles, let's think about the kind of average albedo of like a tundra environment. Tundra environment might have an average albedo of about like 30%. Okay, so that means that 30% of the incoming solar radiation that hits a tundra is reflected, and about 70% of it would be absorbed. Now let's think about the average albedo of water, of like ocean water. So the average albedo of ocean water is actually quite low. It's only about 10%. So that means that the oceans absorb about 90% of the incoming solar radiation and reflect about 10%. Okay, how does that compare to the albedo of ice? The albedo of ice is a whopping 85%, give or take. It can vary, but it's much, much higher than sort of, average continental grassland or tundra or ocean water, right? So 85% of the sunlight that hits ice is reflected off of that surface. This means that the growth of ice sheets switches on something called a positive feedback loop. Okay, so if anyone who plays the guitar, the electric guitar, will be familiar with that horrible screeching sound that comes out of your amplifier if you point the guitar towards the amp. So this can also happen, with any microphone. So if you've ever been to a sporting event or like any sort of, event with a sound system and you hear that shrill screeching, what you're hearing is called feedback. And what happens is the signal from the guitar or from the, speakers enters the microphone and gets amplified again, and then it enters the microphone again and gets amplified again and again and again. And eventually that signal just turns into this high-pitched, horrible screeching noise. But so a positive feedback loop is any process where the thing that's causing changes causes other changes that amplify the effect of the original change. It's kind of hard to explain, so let me draw out an example involving ice and albedo. Okay, so as ice appeared in Antarctica starting about 30 million years ago, we had a cooling climate. Earth's climate was cooling because of the drawdown of atmospheric CO2 from chemical weathering of the Tibetan Plateau. Okay, so this cooling climate created a situation where we could grow more snow and ice. Okay, once we grow more snow and ice, that snow and ice has a much greater albedo than either the ocean water or the tundra that used to be in its place. that increases the albedo of the Earth's surface where that ice is formed. And that, in turn, causes less solar radiation to be absorbed. That less solar radiation is being absorbed, right? More is being reflected. That causes the climate to cool even further. Okay, so the climate keeps cooling further. That makes more snow and ice. The albedo gets even higher. Less and less radiation is absorbed, right? So you can see how this process establishes a positive feedback loop where the more ice that grows, the colder it gets, allowing more ice to grow, and it gets colder and colder and colder. It's a positive feedback loop because each step in this process amplifies the effect of the next step. It's a positive feedback loop. The real importance of this positive feedback loop becomes clear when we look again at our polar geography. So consider Antarctica, sitting at the bottom of the planet there. Once Antarctica starts to glaciate, that positive feedback loop makes it get covered in ice very, very quickly, right? And that's what we see in the benthic foram record, is a very sharp drop, very sharp change on that plot where the oxygen 18 values increase very quickly. And that's because this positive feedback loop allows the glaciation of Antarctica to happen really quick, just boom, spreads out in all directions. But once the ice on Antarctica hits the edge of the continent, it's pretty much stopped in its tracks, right? So it can't really expand into the ocean, beyond Antarctica, because we know that sea ice is unstable. So there's certainly sea ice around Antarctica that would expand and contract, but it can't stick around long enough to spread to South Africa or Australia, right? It's stopped by the oceans. But in contrast, if we look at the northern hemisphere, right, once ice is able to establish itself on the very northern parts of Asia and North America and Greenland, then its real estate is wide open, right? It's got all of North America, all of Asia and Europe, right? It's got this huge land masses available to it. So once it gets over that initial hump, that ice can really, really expand outward. In fact, during the last glacial maximum, the Laurentide ice sheet sort of came down all the way into North America like this, covered all of Greenland and Iceland and much of Europe. And a lot of northern Asia as well. So this whole area then became available to be glaciated once the ice albedo feedback loop could get going. But you can see in contrast, Antarctica is sort of stuck. The ice can't get any bigger. So back to this feedback, this positive feedback. The ice albedo feedback serves to increase ice, right? So it makes the climate even cooler, grows even more ice. But this same feedback can also work in reverse. So a warming climate would cause less snow and ice, which would decrease the albedo at the poles, cause the poles to absorb more solar radiation and continue the warming trend, right? So even though in this case, this feedback is kind of decreasing the volume of ice, we would still consider this a positive feedback because the overall effect is that each process amplifies the next one. So if we have these two feedback systems, One that serves to, amplify the amount of ice that's forming, make it colder and colder and colder, make more and more ice, and then another one that causes ice to melt faster and faster and faster. This ice albedo feedback. If both of these feedbacks exist, how is it that the whole Earth doesn't either just get covered in ice and stay that way, or have no ice and stay that way, right? There must be some other process that is influencing those two feedbacks or modulating them, right? So it's another process that's controlling which one of those feedbacks is going to take charge, right? Which one of them is going to be most powerful. So moving forward, we're going to explore the process that modulates these two feedbacks, or it's really just one feedback, the process that modulates this feedback system. But in order to do this, we need to explore the climate record on a higher resolution than the benthic forams. So this plot takes us from over 60 million years ago to the present, but to understand the process that modulates the ice albedo feedback, we're going to have to get a higher resolution record, so a smaller slice of time. We're going to expand that small slice of time to look at it in greater detail, because we just can't see the detail that we need on a record that's this long.